Hello, Eastview Scholars, and welcome to this edition of Sharp Shorts. We're going to continue on our discussion of stoichiometry here and add in limiting reactants. Okay? And I have a very simple question for you, just the same as I gave you in class. But if you were to book a plane, we know airlines do this all the time. They overbook flights. So the plane has 350 seats. But 400 people actually show up with tickets and want to fly. How many get to go? Well, you know the answer to that. It's 350. And there's just no more room on the plane. They're not going to stuff anybody in a cargo hold. There's no heat in there. And at 30,000 feet or whatever, at minus 70 degrees, they would not survive very long. It's the same thing in chemical reactions. We've kind of led you to believe or thought about at the moment that you put these reactants together and a reactant occurs and everything just happens and you get products. The reality is, because of their mole ratios, oftentimes, particularly if one of the reactants is very easy to remove from the products and very inexpensive, is that you would focus on just one of those reactants you start with, maybe the expensive one, and use that to control the reaction. There are times when both reactants run out at the same time, but that's in a sense that's really more rare. And so what the limiting reactant is the one that runs out first. And if you think about it, we'll have an example in a minute. If you think about that, you have these two reactants, or maybe you have three or whatever. But you have these two reactants, and you put them together, and one of them runs out, the reaction stops. There's nothing to interact with anymore and swap, say in a double replacement, swap cations and anions and anything. It's just done. And that will happen even though you still have some of the other reactant left over. Then that you just filter out away from the product and stuff, but that's our excess reactant. So the limiting reactant is the one that runs out first, which stops and controls the reaction. The excess reactant is the one that still has some left over when the reaction stops because you had more than you had for your limiting reactant. Okay. That's a key because in your calculations, the only one you can use to calculate how much product you would make or percent yield or other stuff is the limiting reactant. So let's go to our example. Here we have a reaction here. Double replacement, aluminum chloride. 1 mole of aluminum chloride interacts with 3 moles of sodium nitrate to make 1 mole of aluminum nitrate and 3 moles of sodium chloride. What I'm going to do is figure out how much of each of these did I make. Now, I'm starting with 200 grams of aluminum chloride and 350 grams of sodium nitrate. And I've set up my stoichiometry grid. Here's all the molar masses of everything. The first thing I have to do, like I always do in stoichiometry, is just convert both of these masses into moles. And then I'm going to find out which one is the limiting reactant, and that's the one I have to use because that's the one that's going to run out. Okay. So in the first step, 200 divided by 133.5 is, to three significant figures, 1.50 moles. Okay. Now, for this reactant, 350 grams divided by 85 grams per mole is 4.12 moles. Now, at first glance, you're going to say, well, this aluminum chloride sure appears to be the limiting reactant. It's got less moles, and those are going to get used up in the interaction here, and it's going to stop, and it's going to be gone. And that would be a pretty valid guess at times, but remember, the mole ratio here is 3 to 1. You need 3 times the amount of moles of sodium nitrate as you do aluminum chloride. If you don't have 3 times the amount, then you're not going to. Then this can't be the limiting reactant. It would have to be this one. Okay. Now, how do I know that? This would be true if these had the same coefficient, but they don't. So how do I check? Well, I just go off to the side of my paper and I divide the moles I have. So for the aluminum chloride, it's at 1.5 moles. And I'll divide that by the coefficient from the balanced equation, which is 1. and 1.5 divided by 1 is 1.5. Okay? All right. Now, I do the same thing for the sodium nitrate. Off to the side, I take 4.12. Oops, sorry for the writing. I divide that now by 3, because that's the coefficient it has to denote the 3-to-1 ratio. That number is actually 1.37. So while it's not by much, what you actually see is I don't have, 3 times this amount would be 4.5 moles. I don't have 4.5 moles. I only have 4.12. So in all reality, and this was my check, getting them on a 1-to-1 kind of basis, this is my limiting reactant, the sodium nitrate. Okay. The importance then means that this, I cannot use this. This must be the moles I use to figure out the amount of product that I'm going to get on each of these. It has to be this one. Okay. There was leftover here. Okay. This one ran out. There was still leftover here. So anyhow, then my normal stoichiometry kicks in. I have 4.12 moles. This is a 1-to-3 ratio, so 4.12 times 1/3 is 1.37. So that's how many moles of aluminum nitrate are going to be produced. These two have the same coefficient, so 4.12 times 3/3, or times 1, is 4.12. Okay. All right. And then I just multiply by my molar mass. So 1.37 times 213 is 292. So that's how many grams of aluminum nitrate will be made. And 4.12 times 58.5 is 241. All right. The key to it is, I first have to look, I have to divide these into moles. I have to figure out which one's smaller. And if they don't have the same coefficient, I need to divide each by its coefficient to really see which one is smaller. Now the question is, how much leftover do I have? This is my excess reagent. A certain amount of this 1.5 moles is going to be used in the reaction to produce these products. This is going to run out, that's going to stop. So the question is, how much is left over? Well, here's what I know. Okay? It's a 3-to-1 or a 1-to-3 ratio. So 4.12 times 1/3 is 1.37. So here's what I started with, but what I actually would have used is 1.37. Okay. That's how much I used from the start. So if I just take the difference, you can see that 0.13 moles of this is going to be left over. Okay. And I can convert that into grams very easily. I just multiply by the molar mass and find out that that equals about 17 grams. Okay. It's the same stoichiometry, but again, I have to use this moles to find this one with my mole ratio, this one with my mole ratio, and then here I can figure out how much was used, so I can find out how much was left, and I can convert that into grams and see how much was left over. Okay? So that's the basics. Again, whenever you're given, here's my 2 reactants, and whenever I'm given the mass of both, I convert them into moles, and then I see which one is smaller, making sure, if I have to, that I divide each by its coefficient to figure out which one's a limiting reactant and use that only to do the rest of my stoichiometry calculations. All right? There you go. Go practice some problems. Scholar up, East View. Our next discussion will be percent yield.